So we start here. In a typical electronic system, this is often in a microprocess cooling. To be specific, is that we always deal with what is called a junction temperature. The junction temperature is measured at the die level, and then there is a thermal interface material often placed between the die and the integrated heat spreader, which is a copper material, and that integrated heat spreader is required in many occasions because the die itself is dissipating about 100 watts, but if you assume the area of a die is 1 centimeter by 1 centimeter, that gives about 100 watts per centimeter square. So to give you a perspective, if you look at a common bulb that is used in household, the bulbs also dissipate about 100 watts, but then the area is on the order of if you calculate, it's on the order of 0.1 or 0.1 centimeter square. So the flux levels that often a bulb sees is only on the order of 1 watt per centimeter square, but these processes see about 100 watts per centimeter square. So that makes it, the flux needs to be spread into a larger base, because air cooling, if often used for cooling these devices, are incapable of dissipating heat because of lower heat transfer coefficients, and that some of the coefficients and the discussions you may have had in the previous lectures we'll cover these little bit again. But then the heat sink needs to be dissipated over a large area, and so the heat needs to spread from a smaller area of a die to a larger area of a spreader. And on top of a spreader, often a heat sink is placed. The heat sink can also be much larger than the spreader itself. So this spreading resistance is often needed, or the spreading is needed, and the spreading is often referred by what is called a spreading resistance, and we cover that in the next few slides. And anytime heat flows from a smaller area to a larger area, in addition to the bulk conduction resistance, one has to account for what is called spreading resistance. So to come back to this resistance network, one has a resistance between junction to the integrated heat spreader, where there is a thermal interface material. On top of it, there is also a spreading resistance here. The thermal interface material mitigate what is called the contact resistance between the two materials. When you put two materials together, as we discussed in the previous module, there is microscopic peaks and valleys. Peaks are the ones that are actually making contact with the other material. Because of the microscopic peaks and valleys, now the apparent area, the actual area that is in contact when you don't apply any pressure is estimated to be only 1% or 2% of the overall apparent area that we see visually. If, for example, if it is 1 centimeter by 1 centimeter and you make contact with 1 centimeter by 1 centimeter another material, the phase area that is actually in contact is only 1% of that 1 centimeter by 1 centimeter. So one puts what is called this thermal interface material to reduce or improve the contact area. On top of it, provide a thermal conduction path between the heat generating source, which is the silicon die in this case, and the integrated heat spreader, which is the copper. So one has in the resistance network between junction to the die to the case or the integrated heat spreader is that one has in the resistance lumped conduction resistance, a spreading resistance, and thermal interface material resistance, bulk, as well as the contact resistance between the thermal interface material and the silicon die, and the contact resistance between the thermal interface material and the copper heat spreader or the integrated heat spreader. So the next resistance that is often drawn there is the integrated heat spreader and the ambient. So if you have a heat sink, then the heat sink and the integrated heat spreader often is abridged, sandwiched by a thermal interface material. Again, all those are clubbed into one resistance node, and that is called the junction or case to ambient resistance. And this is the common terminology that is used in the electronics industry to capture some of these aspects again. Between the integrated heat spreader and the ambient, you see that there is contact resistance between the integrated heat spreader and the thermal interface material, bulk resistance of the thermal interface material, and the thermal interface material and the heat sink itself. And on top of it, in the heat sink, there are other resistances, that is the conduction resistance through the fins at the base of the heat sink, then the conduction resistance in the fins, then convective resistance from the fin to the flowing air if air happens to be the ambient that is cooling the system. So there are so many number of resistance, and they are all clubbed into these two resistant packs for convenience. Otherwise, each and every time one deals with one has to represent all these resistances. On top of it, there could be a spreading resistance from the integrated heat spreader to the heat sink as well, if the heat sink size is much larger than the integrated heat spreader size. So moving on, and to give you a perspective, if I look at, there is a card that is shown here, which is called Intel Xeon Phi or Knight's Corner. This is one of the add-in cards that Intel pushed to market. And if you look at the thermal packaging architecture, there are so many different types of elements that are involved here. So there is a heat sink. This is the overall system design becomes extremely challenging affair. The add-in card is shown in green, and that is the Knight's Corner package, and it has processor, it has memory devices and so-called voltage regulators and power connectors and so on. And one of the zoom up of this, if I look at this so the VCR is the voltage regulator, the GDDR is the memory device that is used there, and KNC refers to the processor. So these memory devices are also placed on the back side of these add-in cards. So if you look at, there is something called power connectors, 12 volt power, that is shown on the right side, and that is where the card receives its power from the server board, for example, or the workstation. So the power comes in, it's a 12 volt power that comes into that card, and through what is called VCRs, which is the voltage regulators, gets converted to the requisite voltages for the memory devices and the microprocessor themselves. So because there is power conversion or voltage step down, there is always inefficiency associated with those voltage step downs. Inefficiency of those voltage step downs shows up as heat, and that needs to be cooled. So one has to cool the voltage regulators. Then the memory devices, they also consume power, and so they need to be cooled as well. And most important is also the processor, that also needs to be cooled here. So one sees that if you look at the larger packaging architecture, it is completely filled with heat sinks and materials, that there is absolutely no space for adding any other features, or one has to be very tight. And one often, when designing these cards and other things, one always worries about even a millimeter of gap if someone can provide. So one of the challenges in this card is that the backside of the card is also dissipating heat, but because of standards used in designing these systems, the backside cannot have any room that you wish, but it is limited to a certain space limit that is less than some 4 millimeters or so. So there is no way to flow air on the backside of this motherboard, this add-in card. And so what in this architecture one does is that one conducts heat from those memory devices from the back and brings it to the top where the airflow is happening, and it is cooled that way. So when designing these thermal designing of these systems involves a lot more than just doing some Reynolds numbers and calculating a heat transfer coefficient. So one has to be aware of where the heat is generated and where it could be dissipated. So remote heat sinking is a very common thing in electronics industry, and if you see in laptops as well, there are so-called remote heat sink, because where the fan is, where the processor is, there is no sufficient room on top of it, so one cannot mount a heat sink there because the laptops are shrinking in size, overall size as well, so one has to shrink. So that means you have to carry the heat to a location where you can mount a heat sink and a fan, and that is why you see that they are quite one has to come up with devices that allow for efficient way to carry heat from location A to location B without adding much resistance to the thermal path. So those are the aspects that we'll discuss briefly. And now from a generic perspective, the modes of heat transfer that are involved in this process are conduction, convection and radiation, that I am sure you are well aware of. Whenever you are talking about convection, there are two forms that often we talk about. One is the natural convection and the other one is the forced convection. When you look at a smartphone, there is no fan in such a smartphone system. So all you have is natural convection way of doing. Typical natural convection heat transfer coefficients are on the order of 5 watts per meter square Kelvin. And if you imagine that the cell phone, for example, is on the order of 100 millimeter by 50 millimeter face area, then the dissipation that one can achieve with 5 watts per meter square Kelvin is going to be only on the order of 3 to 5 watts, because there is an ergonomic limit as well in thermal designing these smartphones. The touch temperature of these devices cannot exceed 41 degrees or so. That is the ergonomic limit. If it exceeds 41 degrees, you can't even hold the phone. So that's why the skin temperature, the phone temperatures cannot exceed a certain ergonomic limit. So that makes the temperature driving forces to be small as well. On top of it, one uses only natural convection. When you are talking about heat dissipation by natural convection, often you find that radiation becomes an important contributor. So when looking at thermal design of smartphones and handheld devices, you often rely both on radiation as well as on natural convection cooling. So we'll look into some design or more interesting concepts. How do we define a thermal resistance? I have depicted here in this slide two situations. One has a uniform heat source mounted with a heat sink, and the other one is a smaller heat source mounted on a heat sink. The thermal resistance by definition is voltage difference. In this case is the temperature driving forces divided by the current that is passing through it. Current here is the heat transfer rate or heat flux. Here we use heat transfer rate, and temperature difference by heat transfer rate is the thermal resistance. T hot often refers to the hotter junction, and cold refers to the colder part. In this case, if the heat sink is used, then there is the ambient, that is the cold. And so TH minus T hot. In situation number 1, which is on the left hand side, you see that it is a uniform heat source. For a uniform heat source, the identification of a hot temperature is quite easy, because the temperature is going to be the hot temperature will be uniform, because the heat sink covers the entire heat generating device. The T cold is fixed at the ambient temperature, so there is no confusion. But if you look at the right hand side picture, now your heat source is much smaller than the heat sink. So which temperature is the right temperature to choose for hot? Is the maximum temperature or the average heat source temperature? So the question is how to choose it. Is maximum the right quantity or the average? While the industry wants maximum temperature, but thermodynamically we cannot define a resistance based on a point temperature and an ambient, which is a larger reservoir. A temperature resistance is often defined between two reservoirs that are maintained at isothermal temperatures. So to be accurate, one always defines the resistance as the hot temperature will be the average temperature of the heat source minus the ambient temperature or the T cold divided by the power dissipated by the heat source. So, to give you a perspective, here is a picture of the same smaller heat source and some temperature profiles are shown. Is that the Q is generated uniformly in the small heat source. The peak temperature has that, you see the maximum, it is referred to as T max comma source, T average is shown as dotted lines, and the heat sink level there is an average bottom temperature. So, one refers to the temperature resistance as the thermal resistance as between the average temperature of the heat source minus the average temperature of the heat sink base as one resistance network, and then from average resistance of the heat sink base to the ambient temperature. So, these are the right way of defining these, and if one defines based on max temperature, then we are probably not conserving the energy or the heat transfer rate. So, it is best, even though the industry would prefer to know the maximum temperature, that is the temperature we do not want the device to exceed, it is best to define based on these average temperatures and then figure out a way to predict the maximum temperatures. So, we need to discuss little bit more about the resistance concepts, and as I discussed just for the last two slides is that we have thermal resistance typically referred as T hot minus T cold divided by the power dissipated by the heat source. And if there is the conduction is a dominating mode of heat transfer, then one defines conduction resistance as the thickness L of the block. Let us look at the image on the screen. So, one defines conduction resistance as L by Ka. A is the cross section, AC is the cross section of the conduction heat transfer, and this is equal to T hot minus T cold divided by the power that is passing through this rod. So, on the other hand, as I mentioned, the contact resistance is always there between any time you have a composite structure like a typical microprocessor cooling stack, is that now one has to worry about it. A contact resistance, unlike thermal conductivity, which is an intrinsic property of the material, contact resistance is not. So, it is often measured empirically and documented in a database. So, the experiments cannot be done for any kind of area that one in, because the area of contact changes from application to application. So, often the contact resistance is written in a form of, is tabulated in the form as RC double prime divided by the A contact. Contact is the contact area, that is the projected area of the surface, ignoring their microstructure. And R contact double prime is area specific contact resistance. So, when you take that area specific contact resistance and divide by the actual area that is of interest to you, then you obtain what is called the contact resistance between those two materials. So, one has to be careful in choosing those contact resistance because they should be compatible with the material set that you are dealing with. Then the last one or the next one is the convection resistance, which is often defined as 1 by heat transfer, mean heat transfer coefficient times some surface area of the material that is in contact with the flowing medium. This heat transfer coefficient is a very challenging task in electronics, as we will discuss later in the modules, in the upcoming modules, but one really has to be very careful about choosing these heat transfer coefficients, and how to choose them in a given situation is extremely challenging. And the last one is the radiation resistance, and that is often covered, and it is shown here as 1 by surface area for radiation, sigma times epsilon. Epsilon is the emissivity, sigma is the Stefan-Boltzmann constant, and T is the average temperature, that is T hot plus T cold divided by 2 raised to the power 3 is an approximate relationship that is often used for radiation resistance. So these make up a resistance network. What is shown on the top of is that, as we discussed, maximum temperature versus average temperature. What is shown on the top one is the steady state resistance network, but if one is interested in knowing the transient part, then one has to write RC network, that one has to calculate the capacitance of these materials as well and assemble them into a RC network, which is the resistance capacitance network. We won't be talking about these RC networks, but we'll just deal with the resistance network briefly in this. The spreading resistance, as we discussed, anytime heat flows from a smaller area to larger area, it is often one additional resistance need to be accounted for, and that is the so-called spreading resistance. And if the heat flows from a larger area to a smaller area, it is called a constriction resistance, that is, the heat flow is being constricted to flow through a smaller area. And one adds this spreading resistance to the bulk resistance to obtain the overall thermal resistance of such a system where heat flows from smaller area to a larger area. As we see that always when cooling a device where heat is generated, even though you may have same amount of power dissipation from the for example, the shown picture where left hand side has the same power as the one on the right hand side, where a smaller heat source is placed on the same size of a heat sink, while on the left hand side the heat sink size and the heat source size are equal. When the power is equal, cooling the right hand side is much harder because the heat flux is very, very high compared to the one on the left hand side. So that's why one in microprocessors and many electronic devices which are often shrinking, but the heat carrying capacity of air is limited by its specific heat, that dissipating beyond a certain power levels becomes almost impossible, and that's why water becomes a realistic medium for cooling. And that's why in high performance supercomputing devices, because of this heat generation at a smaller from a smaller heat source to a larger heat source becomes extremely challenging. Here are some occasions in some interesting pictures from electronics, motherboard and others, that if there is no space, then often heat is dissipated through the substrate to the motherboard and through the motherboard on the back side as well. And you can see some instances of spreading and constriction resistance shown in these pictures. So one last question: what happens to average temperature of the heat source as we change the size of the heat source? So you can see there are series of images from left to right. One has the heat source size is same as the heat sink size, but the heat source size shrinks as we go from left to right. The average temperature does not change in any of these. The only change that happens from when we go from left to right is that the peak temperature increases as we move from left to right. The average temperature of the heat source does not change in any of these situations. So when you have a situation that I've been talking about, which is a smaller heat source mounted on a base plate of a heat sink, and the thickness is, let's say, is T, then you see that spreading resistance is often couples with the heat transfer coefficient. Heat transfer coefficient here is that on the bottom of the base conductive substrate, you see some airflow happening, or some sort of a heat transfer airflow or any fluid is happening, and you see that there is a heat transfer coefficient H shown there, and as air is flowing, the heat is carried away by the air that was generated by the heat source. So there is always a direct coupling between the spreading resistance and heat transfer coefficient. Many of these problems is that what is shown on the left hand side, let's take for example the silicon plot that is shown. There is R thermal versus, that is the thermal resistance from the heat source all the way to the ambient, and versus heat transfer coefficient. You see that it is shown in decades. The horizontal axis is a log plot. So the heat transfer varies from 1 watt per meter square Kelvin to all the way to 10 power 5 watt per meter square Kelvin. You achieve on the order of 10 power 5 watts per meter square Kelvin using boiling type heat transfer, but 1 watt or 5 watts is often achieved in natural convection cooling type systems. And when you have a fan mounted air cooled systems, you get up to 100 plus watts per meter square Kelvin. So when you are moving from all the way from 1 watt per meter Kelvin to 100 watts, you see the change in resistance, thermal resistance is only about half. For example, for the thickness of 750 micron, the change in resistance, so even though your cost has gone up so incredibly, the change in thermal resistance is only half. Because you are putting fans now, you have a fan that is a cost adder, and you have to put larger heat sink and so on. Even though your heat sink size has increased, fan size, the improvement in thermal resistance, having moved from natural convection to forced convection air, is only half. But if you go further to the right, going from 100 to 1000 or even 10 power 4 watt per meter square Kelvin, the change is even less. That means the primary problem here is the spreading resistance. You can provide as many complex cooling technologies, but it is not going to change or improve your situation unless you address the spreading resistance. How do we address the spreading resistance? That is typically by improving the thermal conductivity of the conductive substrate in this case, for example. Improve the thermal conductivity of this conductive base, then you mitigate the spreading resistance. That is, the heat is able to spread much more readily than in the case when the thermal conductivity of the substrate material is poor. For example, if you move from cast aluminum to copper, you have almost 4 times improvement. Cast aluminum thermal conductivity is on the order of 100 watt per meter Kelvin. So if you move from 100 watt per meter Kelvin to 400 watt per meter Kelvin, you get very significant improvement in spreading resistance. But there are occasions where one has to even improve the copper thermal conductivity, and that's when one uses what is called vapor chambers or heat pipes. Their thermal conductivities are almost 3 to 4 times better than the copper thermal conductivity. So that's where we stop here, and we'll pick up about some interesting aspects of these in the next module.